This conference will now be recorded.
This is a software demonstration video to demonstrate use of the Kendall-Teal Robust Line program documented in U.S. Geological Survey Techniques and Methods Report TM4A7. This program and the related documentation was prepared by the U.S. Geological Survey in cooperation with the Federal Highway Administration, Office of Natural and Human Environment. This video, which takes about 25 minutes, demonstrates use of the interpretive graphing and models. The interpretive graphing and model specification form appears once the user has entered all required information on the input data specification form and clicked the Graph Data. The interpretive graphing and model specification form is designed to facilitate graphical examination and interpretation of the data, the line, and residuals. The graphical display has several components. The primary component is the graph of the data and the estimate of the Kendall-Teal Robust Line. The column heading information is displayed on the X and Y axis of the graph. The graphical display has a label in the upper right corner to indicate what. The explanation to the right of the graph also provides information about the contents. In this case, the explanation indicates that the XY data are plotted with the Kendall-Teal estimate of the line. The transformation status title in the lower right corner of the graphical display interface indicates the transformation status of the X and Y data on the plot. If the data are not transformed, as we see here, the transformation status title will read X and Y. This explanation will change independently as either the X and Y or both are transformed to linearize the relation. Interpretive graphing and model specification form has X and Y population statistics, the equation of the line, and residual statistics on the form under the one line. The median of slopes, the intercept, and the equation of the line are apparent in the lower left corner. Regression statistics, such as the root mean square error, the number of ties and x values, the median error, the median absolute deviation, or MAD, the bias correction factor, or BCF, and the non-parametric prediction error sum of squares, or PRESS, are apparent in the lower right-hand corner of the form. The interpretive graphing and model specification form has a number of tools to facilitate graphical examination of data. The data identification tool is not visible on the form, but it can be activated by left-clicking. This activates a pop-up message box that provides information about data on the graph. In this case, the value of the X and Y data points, the KTRLINE estimate, the error or residual value, and the metadata, including the station number, date and time of sample collection, are displayed on the message box. If the wrong point was selected or the user does not wish to save the information to the output file, the user should click the No command button. In this case, however, we may wish to save this outlier for further study, so we will click Yes to save this information to the output file. Another tool is the Adjust Data Point Size slide bar on the upper right side of the interpretive graphing and model specification form. This allows the user to change the size of the data points on the graph. The user may increase the size of the points by moving the slide bar downward on the form. The user may want to increase the data point size to better distinguish between adjacent points with similar but not equal XY values. The user may wish to decrease data point size to better distinguish among a group of points clustered in one part of the graph. The user also may wish to increase or decrease the data point size to facilitate point selection. There are four related tools immediately below the graphical display interface that control the range of x-axis values displayed. These tools are, from right to left, the Scale By option box, the Rescale x-axis to the slide bar values command button, the Set Desired x-axis range as a percent of total range of data slide bar box, and the Rescale x-axis to the default values command button. The top slide bar controls the lower limit of the data displayed in the graph. The bottom slide bar controls the upper limit of the data displayed in the graph. The user can adjust the percentage of the range that is displayed by left-clicking on the pointers and dragging them up and down the scale. The percentage values will be displayed as the pointers move. Then, to rescale the x-axis, left-click the Rescale x-axis to the slide bar values command button. The x-axis is rescaled to graph the reduced range of data. Environmental data sets are commonly skewed, and rescaling by the percent of range may not indicate the percent of data in that range. Therefore, the program provides the option to rescale by the percentiles of the data. Once this selection is made, left-click the Rescale x-axis to the slide bar values command button to regraph by the percentiles. X-axis allows the user to examine different ranges of data and facilitates point selection. In this example, the line looks like a poor fit for the top half of the total range from 2,000 to 4,000 cubic feet per second. Rescaling by the percentile of data, however, indicates that the line looks like a good fit for more than 90% of the data. To readjust the graph, left-click the Rescale x-axis to default values button at the Interpretive Graphing and Model Specification form has three tab strip menus on the upper left side of the form. These are Plot, Transform, and Specify. Each may be activated by clicking on the desired tab. We will examine these menus and will start with the Plot menu, which is the primary menu. The default choice on the Plot menu is the Data Radio button. When the Data Radio button is selected, the graphical user interface will display the input data and the current regression line. These selections on this menu are designed to facilitate graphical data exploration and regression model specification. As such, the user may display the data, QNAME plotting positions expressed as percentiles of the X or Y data, regression residuals plotted as a function of X or as a function of the predicted value yp, or the QNAME percentiles of the residuals. We have seen the data plot. Now let's look at the percentiles of the X. Activating the X percentile radio button changes the contents of the graphical display interface. The data are sorted and ranked. The values of the X data are displayed on the X-axis, and the QNAME plotting position percentiles are displayed on the Y-axis. The label in the upper right corner of the graph indicates that we are looking at QNAME plotting positions. The explanation indicates that the X percentiles are plotted, and the transform status title in the lower right corner indicates that data are not transformed. If the discharge data were normally distributed, the percentile graph would be symmetrical on each side of the median and would be characterized as a diagonal line with the lower and upper tails that approach the 0 and 100th percentiles asymptotically. In this case, we could see that the population of discharge values has a substantial right skew. Now, let's look at the percentiles of the Y population. The graphical display interface changes to plot the Y population. The X-axis label changes to indicate that we are looking at the plotting positions of the Y data, suspended sediment concentrations, and the explanation on the graph indicates that the Y percentiles are plotted. If we were to activate the data identification tool, plotting position values would be displayed. This graph indicates that suspended sediment concentrations also are right skewed. Now let's look at the regression residuals plotted as a function of the X values. The graphical display interface changes to plot the residuals versus X. In this case, the X-axis label indicates that discharge is being plotted. The Y-axis label indicates that the residuals are being plotted. The label in the upper right indicates the type of plot, and the explanation indicates that we are looking at the population of residuals. Examination of residuals is important for development of a good regression model. Residuals should be centered around 0 and show constant variance throughout the range of X values. In this case, we see increasing variance with increasing discharge. Now let's look at the residuals versus the Kendall-Teal robust line predictions for Y. Again, the X-axis label and the explanation change to indicate the contents of the plot. In this case, the line has a positive slope, so the plot of residuals versus Y looks like the plot of residuals versus X. This plot still provides valuable information. For example, the outlier in the upper right quadrant of the graph is more than 10 times the predicted value of about 20. Although this is a high leverage outlier, the magnitude of the value does not affect the robust Kendall-Teal estimate of the regression equation. Now let's look at the plotting positions of the residuals. When the plot for the percentiles of residuals is selected, the graphical interface changes to indicate the contents of the graph. In this case, residual errors are sorted, ranked, and plotted against their cunane percentiles. The graph of cunane plotting positions of residuals also is useful for graphical regression model development. In this case, we see substantial skew in the top 10% of residuals. Throughout the model specification process, the user may click back and forth among the graphs on the plot menu and use the data identification tool to examine the input data, predictions of the line, and the residuals. Now let's return. Examination of the data, the KTRLINE, and the properties of the residuals indicates that a transformation of the input data may be useful for developing a better linear regression model data. Therefore, we will proceed to the Transform tab strip menu. The user can independently choose any of the transformations within the ladder of powers on the Transform tab strip menu to find a transformation that linearizes the relation between the x and y data. The natural or common base 10 logarithms are most commonly used for environmental dataset. In this case, we'll look at a log transformation for both x and y data. Large datasets can take several minutes as the data transformations and regression statistics are recalculated. Therefore, the software does not do the transformation until the user left-clicks on the Transform Data command button. If the dataset is large, a progress bar will be displayed while the data is being transformed. When the transformation is complete, the Plot tab strip menu is activated and a message box pops up reminding the user to save the transform regression model to the output data file. The program does not automatically save a new regression model because the user may try and discard one or more transformations before identifying a satisfactory model. Once a transformation is selected, the graphical user interface changes to plot the data in transform space. The x and y axis explanations are modified to indicate the transformation, and the label in the lower right corner indicates the transformation status. Finally, all the statistics are displayed as transform values, and the equation of the line is modified to show the new equation in transform space. To save the results of a transformation, we left-click on the Save One-Line Model to File button. A message box will confirm the selection. Examine the data and residuals after transforming the input data. Examination of data indicates there may be random variation in suspended sediment concentration below a discharge of 1,000 cubic feet per second, a log base 10 value of 3, and a strong upward slope above this threshold. The log-log Kendall-Teal regression model does not look like a particularly good fit in either of these intervals. We should, however, look at the distribution of data and residuals. The plotting position graph for the discharge data indicates that the transformation has reduced the skew apparent in the untransformed values. Let's look at the plotting position graph of the y data. The plotting position graph for the transformed suspended sediment concentrations also exhibit less skew than the untransformed data. The transformation, however, reveals that suspended sediment data are reported with a precision of 1 milligram per liter. That is why the graph of plotting positions is discontinuous in the x-axis. Because the data range more than an order of magnitude, however, we may treat the values as continuous data for the purpose of developing a water quality transport curve. Now let's look at the plot of the residuals versus x. The plot of residuals versus x confirms that there is non-constant variance in the residuals with respect to x. The downward slope in residuals below 1,000 cubic foot per second, a log value of 3, indicates that a positive slope regression line may be unsuitable for predicting concentration from discharge in this interval. The sharp upward slope apparent in the upper range of data indicates that the one-line model underpredicts concentrations above a discharge value of about 1,000 cubic feet per second. Now let's look at the graph of residuals versus the predicted log-log Kendall-Teal regression model values. Because predicted suspended sediment concentration values increase linearly with discharge, the residual versus y plot looks like the residuals versus x plot. As with the other plots in log space, we could see the effect of the reporting precision for suspended sediment concentrations. In this case, it is evident in the parallel lines of residuals. Now, let's look at the cunane plotting position percentile graph for the residuals. Although the log-log model provides a better fit than the untransformed model, The distribution of residuals is still asymmetrical above and below the median residual value. Examination of the data, the line, and the non-constant variance in the other residual plots would lead the user to try a multi-segment model. Now we will click on the Specify tab and explore multi-segment model development. Clicking the tab strip menu brings the Specify tab to the top and resets the graphical user interface to display the line and the data. The Specify Regression Model Segments tab strip has several choices to specify the number of segments and 3 choices for selecting breakpoints between adjacent segments. Now we will select a the Generate Command button is disabled and the 3 interval selection buttons are enabled. The program allows the user to select even intervals, in which case the data are divided evenly into each segment, to select breakpoints from the graph, in which the user sets the breakpoints by clicking on one or more data points, or to enter values for each breakpoint in an input box. First, let's try the even interval button. Now, left-click the Generate Multi-Segment Model command button. The software does all the necessary calculations and launches the multi-segment regression model output form. This form defines each segment, provides regression statistics, and provides an equation for each segment. The scroll bar on the right side of the form allows the user to scroll up and down to see the entire model output. The multi-segment model output also includes total model fit information and a tab-delimited summary of regression model parameters for each segment to facilitate cut and paste into another computer application. The menu at the bottom of the form allows the user to save or print regression model results. Now let's left-click the Save Model Output command button. A message box pops up to confirm that results have been saved. The user can minimize the window or, on a higher resolution screen, move the multi-segment regression model output form to one side to view the graph and the model results, and to compare regression statistics with the one-line model information that's on the lower right side of the interpretive graphing and model specification form. Please note that the prediction error sum of squares is about 54 for this two-segment model. Now we will click the Close button to look at the data and the two. This initial two-segment model indicates that suspended sediment concentrations do vary randomly at lower discharges, and the model fit in the upper half of the data is a better fit than the one-segment model. The prediction error sum of squares, or PRESS statistic, for this two-segment model is 54, which is a substantial improvement over the PRESS value of 64 for the one-segment model. It is, however, unlikely that dividing the data in half would produce the best two-segment model. Let's look at other specification methods. We will try the Select Breakpoints from Graph method. The message box prompts the user to select the desired point or points. Because there is substantial random variability in the data up to and including 1,000 cubic feet per second, a log value of 3, we will select a breakpoint above this value. A confirmation message box appears. The message box provides the X and Y values, and if a transformation is selected, the transform values. The message box also provides the QNAME percentile of the independent X variable. If the user wishes to keep this breakpoint value, they would click the Yes button. If the wrong value were selected, the user may click the No button and try again. We will select the Yes button. Once all breakpoints are successfully specified, the Generate Multi-Segment Model button is enabled and a confirmation message box appears. To proceed, click OK. Then, left-click the Generate Multi-Segment Model command button. The multi-segment regression model output form is activated, and the new regression model statistics are displayed. We can look at these values using the slide bar. This model isn't an improvement on the last multi-segment model, but we will save the results to record the analysis. Before we close this window, let's take a peek at the graph and the Kendall-Teal robust line. Segment model output form. specify a multi-segment model by entering an x-axis data value. To do this, we will left-click the Enter Breakpoints command button. This option allows the user to use overlapping datasets to define segments. Overlapping datasets are considered as more robust for development of multi-segment models. We will select the Yes option. An input box appears for entering the maximum value to be used for calculating the segment 1 regression coefficients. The input box provides the total range of values for the dataset. We will enter the maximum value for segment 1 calculations and proceed by clicking the OK button. The next input box is used to record the minimum data value to be used in the second segment. This box provides information about the total range of data and the range selected for segment 1. Although we typed in the value 3.1 in the last input box, the program automatically defaults to the next lower data value, in this case 3.086. We will type in the lower limit for segment 2 and click OK to proceed. Other methods, a message box appears with the information necessary to confirm our selection. Once all points are selected, the final confirmation message box appears. To complete the process, we left-click the Generate Multi-Segment Model command button. The multi-segment regression model output form appears. Let's look at the model summary information. In this case, we improved the press statistics from 54 to 52. Let's save this model and exit the multi-segment regression model output form. Click the OK button on the output file confirmation message box. Breakpoint or breakpoints for multi-segment regression models is an iterative process. The user needs to look at the data, the line, residuals, and regression statistics including the root mean square error, the median error, and the press statistic to find the best model that can be theoretically justified based on data being analyzed. In this case, we see random variation in suspended sediment concentrations at low flows and increasing concentrations with increasing discharge at higher flows. Now let's look at the residuals with respect to discharge values. The segment model seems to have minimized the problem of non-constant variance in residuals with increasing discharge values. Except for the artifacts caused by the precision in reporting suspended sediment concentrations to the nearest milligram per liter, the population of residuals is fairly evenly distributed above and below zero. Let's look at the regression residuals with respect to the predicted y values. Segment model has a segment with a zero slope. This plot of residuals versus the estimated y values looks more random. The problem of non-constant variance is minimized and the distribution of residuals above and below zero is fairly uniform. Let's look at the percentiles of the population of residual values. The graph of the percentiles of the residuals confirms that the population of residuals is centered on a median value of about zero and is fairly evenly distributed within the limits imposed by the precision of reporting suspended sediment concentrations to 1 milligram per liter. If the regression model is judged to be satisfactory, the user may complete the process by left-clicking the Exit Program command button. The message box appears to ensure that the user actually wants to exit the program at this time. Click Yes to exit and close the program. In summary, the Kendall-Teal Robust Line Program is a robust method for estimating regression line coefficients and related statistics. It facilitates graphical model development by examination of data and residuals. It facilitates data transformation among the ladder of powers, and it facilitates development of multi-segment models to characterize XY relations caused by two or more processes.